So let's move on to section 3.2. This is a section where we are going to basically derive the hydrostatic differential equation. And this is a very important result. Let's take a look at this equation for just a minute. This equation says that for a change in pressure, dP, over a change in elevation of a system that we're looking at in a fluid is going to equal minus gamma. So what this actually means is that if this equation describes how the pressure is going to decrease, that the pressure decreases with actually increasing elevation. So as the elevation in a fluid increases, if we had a fluid here in a container, and this was the bottom of the container at z equals 0, and this is, say, z equals 1 meter or something like that. As you go up in the fluid and delta z increases, that means that the pressure actually has to decrease. They have to be in opposite directions. So no matter what way you're looking at this, delta P, delta Z has to be equal to a negative value, because we know that gamma is positive. It's rho times G. So we have two situations. We can be increasing pressure, but we'll have to be decreasing the elevation in the fluid. Or we need to be decreasing the pressure while we're increasing the elevation, in this case, going up. So we have these two situations, and this is going to help us derive some very useful equations in fluid statics. So let's take a look at this. Just as before, this is just a more general case. Just as before, we see that if it's a static situation, that the net pressure force basically is going to be equal to the net weight, or the net pressure force minus the weight is going to have to be equal to 0. This can be rewritten like this. Net pressure must be equal to the weight, the force of the weight. Or that when they subtract, they have to be 0. So let's go ahead and derive this equation. If you think about this for a second, just think about the forces. I'm going to grab a red pen here. Just think about what's acting on this little cylindrical piece of fluid. We've got this compressive force pressing in on one end, and we have this compressive force pressing in on the other, and we have the weight of the fluid. Of course, we're only interested in the vertical component of that weight, and so you'll see in a minute here that we have a sine alpha that's going to come out of that. The other thing that I want to mention right now before we proceed is that sine of alpha actually equals delta Z over delta L. We're going to need this fact. So that's the opposite side over the hypotenuse, and that gives us the sine of alpha. We're going to need that when we deal with the weight here. So let's go ahead and flip to a new page and derive this equation by just writing down the force balance. So on the left-hand side of the fluid particle, we have P times delta A. On the other side, we have P plus delta P times delta A. Remember that pressure is force per unit area. So if you take pressure times area, as we are in this case, pressure times area, this is actually a force as well as this. And I can see I made a mistake. This is an A. It's delta A. Sorry about that. And if we continue on, this has to be we have to subtract off the weight, and the weight is basically gamma times the the volume. Let me just go down here at the bottom and show you what I mean by that. We know the weight is mg, right? And we can rewrite this equation as being mv over g times the volume. Let me draw a volume like this. So we've just divided by the volume and multiplied by the volume, which doesn't change the problem. But of course, this is rho g, which is gamma. So mg, the weight, is just equal to gamma volume. And so we can write that. We can see from the previous slide that that's what they have written right here is just gamma, right here is just gamma times the volume. And we also need to account for the fact that it's tilted. So we're going to have gamma delta A delta L. That's the area of the cylinder times the length, which is the volume. And we have a sine of alpha. And since it's fluid statics and the pressure forces balancing the weight, these all have to equal 0. Now, look at all the cancellations that we get. Area does not matter. The delta area cancels out. We also have a P minus a P here. We're left with delta P, but these P's cancel out. Actually, it's a minus delta P. So if we go along here, and then also we can plug in sine of alpha equals delta Z over delta L. So let's just recap here. Now we have minus delta P minus gamma delta L, and then sine of alpha, as we saw from the previous slide, is delta Z over delta L. So we also get these to cancel. This is all equal to 0, and we have a very simple formula now that the pressure, change in pressure, equals minus gamma dz equals 0. And we can rearrange this now. Minus delta P is equal to gamma delta Z by just adding the gamma delta Z to the other side and then dividing through by delta Z. We get, let's divide through by minus delta Z. We got delta P delta Z equals minus gamma. And the differential form of this we saw before was dP dZ equals minus gamma. And this tells us again that we have this situation where if the pressure is getting greater than the altitude in the fluid, the height of the column in the fluid must be getting less, or vice versa. It's got to be this is equal to a negative value. Negative value. All right. So let's now use that and define some terms that are very, very important. You will see these throughout the entire semester. The first is the piezometric head, and that just says that we're going to define a value h, which is the head, which is defined to be the pressure divided by gamma plus z. Well, let's just take a quick look at the dimensions of this. Look at the dimensional homogeneity of this. We already know what the dimensions of, if we're trying to find the dimensions here, we know what the dimensions of Z are. That's meters. But if we look at the pressure, we know that that's Newton per meter squared. And we know that the dimensions of gamma are newtons over meter cubed. This gives us 1 over meters plus meters. And we know, as we saw before, that 1 over meter is just a meter. So P over gamma has units of height. And it's basically, we can use this as the head form of this equation in fluid statics. Now we can also keep the units in terms of pressure, and we can define a piezometric pressure, which is going to be basically the compressive pressure inside the fluid plus gamma times z. This is going to be newtons over meter cubed times a meter, which gives us Newton over meter squared. So these are both in pressure now. And typically what we do is we assume constant density inside the fluid, and therefore gamma is constant inside a single type of fluid. So what are the ramifications of this? The ramifications are quite amazing, and that is if we have a situation over here on the right hand side where we had some oil overlaying water, if we look at the piezometric head, or for that matter the piezometric pressure, at any point inside that fluid, they're all equal. HD equals HE equals HF. That means that as we go down in the fluid, the pressure, the gauge pressure might be 0 up here, but you're at the maximum altitude in the fluid. So as you decrease the elevation inside the fluid, the pressure increases, and that's conserved. So the head inside the fluid is always equal. Now, when we go into the water, the same is true. When we go down into here, the head at A, B, and C are all equal as well. But note that the gammas for the two different fluids are not equal. So the head values in the water, the H2O, and the head values in the oil are equal, but they're not equal to each other. So as long as you've got the gamma of water and gamma of oil, as long as you're in a consistent gamma for oil or water in this case, the piezometric head is constant at all locations in the fluid. Very important result. That's going to simplify things for us greatly. So the book gives this nice table which states what these are, and shows that since this is conserved, we have this situation where we can look inside the fluid at two different places and these things will be equal, and we can exploit that to solve problems. We also have the pressure form, which we saw before. And so let's go ahead and solve a quick problem. We're going to apply the hydrostatic equation to find the pressure in a tank. And what is the pressure at a depth of 35 feet inside this tank? We want to choose the situation, a simple situation, so that we can solve the problem. And at the top of the fluid, remember, we can choose the gauge pressure to be 0, equal to the atmospheric pressure. And so if we choose gauge pressure equal to 0, we know what the height is. That means in the head form, we know this side of the equation. And if we're given the depth in the fluid that we want to find the pressure at, we can just solve for P2. So it's a very simple situation. So let's just write that out quickly. What that says is that the piezometric head at point 1 is actually going to equal the piezometric head at point 2. And expanding that out, we have P1 over gamma. Now gamma is constant because gamma, we just have water in this tank. It's just water at 50 Fahrenheit, and that's going to be equal to this. And the head at H2 is going to be P2 gamma plus Z2. And so we want to find P2. So let's go ahead and plug in the values that we know. We can plug in 0 pascals gauge for the gauge pressure at the top of the fluid at the free surface, and then gamma. And we can see, if we look back, that the elevation of this fluid is 250 feet, and we want to find pressure at 2 gamma, and the depth at which we want to find that pressure is 215. Is that what it was? Yes, 215 feet. All right, so solving this, we have this thing drops out, and we're going to have P2 gamma times 250 feet minus 215 feet. Gamma for this fluid in traditional units is, I believe, 62.4. Yes, yep, 62.4. 62.4 pound force foot cubed times 35 feet. And I'm just going to go to a next slide here. And that means that the units we're going to get are pound force over foot squared. And this will be a gauge. This will be a gauge pressure. That'll be gauge. This is also, this same unit is what we call PSF, pounds per square foot gauge. And if we do the math, 35 times 62.4, we get a value of 2184. Now, I wanted to take this opportunity because there were some problems like this on the homework, the first homework, I believe. 2184 pound force per foot squared can be converted to PSI gauge. Remember, this is gauge. This can be converted to this by taking 1 foot squared equals 144 inches squared, and that's also gauge. And what this gives us is the final units. The pound force is still going to be there, but we're going to have pound force over inches squared, which is a PSI, and that also is gauge, PSIG. And this turns out to be 2184 divided by 144 is 15.2. So if we go 35 feet down into water, we are experiencing 15 pounds per square inch pressure on our ears. That's why it's a little hard to go down that far. And so this is it. Note that this conversion factor comes about because 1 foot equals 12 inches. And if you square both sides, you get 1 foot squared equals 144 inches squared. All right, so there's only one other concept that I want to go over for this section, and that is, how do we apply this to the atmosphere? This is an interesting question because all of a sudden we need to use the ideal gas law because the atmosphere is compressible. So gamma rho times G is going to change with temperature and pressure for that matter. So it's a bit more complicated in a gas than it is in a liquid. And so here is the temperature profile of the atmosphere, typical temperature profile for the atmosphere. And we can see that to a good approximation, we can approximate the tropospheric temperature, the lower atmospheric temperature, with a line. And what this is typically shown to be, if I can get my notes out here just a sec. Typically we list this temperature as being the temperature is equal to T0, some temperature, some intercept temperature, minus alpha Z minus Z0. Let me just do that all over again. That's going to be T0 minus alpha Z minus Z0. It's a little hard to cram in there. Now I want to also make the point that this is a line. So you could also write this as minus alpha, where alpha is the slope, times z minus z0 plus t0. So this is the intercept b, and alpha minus alpha is actually the slope. So we're basically creating a linear equation for the temperature, and the slope is a minus value because the temperature is decreasing with height, and the heights are relative to the ground. Z0 is the zero elevation. So given that we can make this approximation, let's take a look at how we apply the hydrostatic equilibrium equation to the atmosphere. So we've got dP dz equals minus gamma, but we know gamma equals rho g, and that's a problem because our density from the ideal gas law, the density form of the ideal gas law is this. So our density actually depends on temperature and pressure. So it becomes RT over, P over RT becomes P divided by RT. So the differential equation, I'm sorry, I think these should have been deltas too, just for, doesn't really matter. But so delta P and delta Z is going to be equal to, in this case, it's going to be equal to minus the pressure times G over RT. So we have a bit of a different equation to solve. And I guess I should have kept these as differentials, because now we have to, the way to solve this is to plug in for the temperature. Remember that the temperature now minus pressure times G is going to be R over this long temperature equation, which is T0 minus alpha Z minus Z0, our linear equation, our linear approximation for the tropospheric temperature. So I'm not going to take the time to derive this, but I will write down the final equation here at the bottom, and what we get if we solve this, if we basically integrate this equation to find the pressure, we find that the pressure at the surface, P0, is equal to T0 minus alpha Z minus Z0, which is our original temperature, divided by the temperature 0, T0. And we have this strange case where we have this all to the power of G over alpha R. So it's kind of a complicated pressure equation. But this is how we can approximate the pressure decrease with altitude in the troposphere, the lower part of the atmosphere. And so to do this, we have an example. Here we say if the sea level pressure and temperature are 101.3 kilopascals and 23 degrees C, what is the pressure at an elevation of 2,000 meters or 2 kilometers, assuming that the atmospheric pressure, the standard atmospheric pressures prevail. And basically they're talking about using this approximation. This is the standard atmospheric conditions. So let's go back here and solve this problem just quickly, and we'll be done with this, this section. So this is really a simple thing to do. We're just going to plug in to the equation, noting that the surface pressure is 101.3 kilopascals. And we note that the temperature equals 23 degrees C, which actually equals 296 Kelvin, because we add 273 to this to get it into Kelvin. And I think that's it. We're also going to use the fact that the exponent of that equation, G over alpha R, turns out to be 5.823. So we just plug in. So the pressure is going to equal P0, 101.3 kilopascals. We'll just leave those units as they are because we're going to multiply times this big factor, which is actually going to, everything's going to everything else is unitless. We'll see in a minute. 296 Kelvin minus 5.85 times 10 to the minus 3 Kelvin per meter. That's the slope of the temperature. Times that factor gets multiplied times 2,000 meters. And this thing is all divided by that 296, and this is all going to be to the power of 5.823. That's a 2, 5.823. So if we take that, basically it's kind of a grubby thing. We've got to calculate all this out, but you can see these are all in Kelvin. This meter is going to cancel this meter, so this is Kelvin minus Kelvin over Kelvin. So this whole thing is dimensionless, and it's taken to a power which is also dimensionless. So this whole thing is dimensionless. So our final answer comes out in kilopascals, and if we do the math, we end up getting 80.0. Now this is kind of a remarkable fact that at only 2 kilometers elevation in the atmosphere, if you go up 2 kilometers in the atmosphere, you are already at 20% of surface pressure. So the pressure drops off quite quickly with elevation. All right, that concludes section 3.2. And the next time, in the next recording, we will go over measuring pressure and talk about different instruments, barometers and piezometers and manometers, to measure pressure in various ways. So thanks a lot.